Hey guys, I'm going to be doing 3 more FE problems. And in this one, it says in the given circuit, determine the value of V3 such that V0 will be 18.5 volts. So let me write down the labels really quick. Okay. So for the first part, you're going to refer to the operational amplifier section in the reference handbook, and we're given no conditions about the op amp, so you can assume ideal conditions. And in the non-inverting terminal, VB is 0, so we can assume the formula V0 equals negative R2 over R1 VA. And then to make an expression for V0, we can see the current through the feedback resistor R2 in the handbook, but we call it RF, is equal to all the currents flowing through the input resistors. No current will be flowing into the op amp because we're assuming that it's ideal. So IF equal to I1 plus I2 plus I3 plus I4, which is equal to negative V sub 1 over R1 plus V sub 2 over R2 plus V sub 3 over R3 plus V sub 4 over R4. So now we can substitute this into the inverting gain equation. So that would be V sub 0 equals negative RF V1 over R1 plus V2 over R2 plus V3 over R3 plus V4 over R4. So as you can see from the picture, it is a summing op amp in an inverting configuration. So all the voltage is running to the negative terminal, and it's summing multiple voltages, excuse me. So now we can substitute the given values, and like it says in the question, so that or just get V3 such that V out is equal to 18.5 volts. So what we're going to do is use that same summing equation. 18.5 volts equals negative 1 mega ohm times 1 volt over 100 kilo ohms minus 4 volts over 200 kilo ohms plus V3 over 300 kilo ohms minus 8 volts over 400 kilo ohms. So then that 18.5 volts is now equal to negative 10 times 1 volt plus 5 times negative 4 volts plus 3.33 V3 plus 2.5 times negative 8 volts. And then 18.5 volts is equal to 30 volts minus 33, or 3.33 V3, where V3 is equal to 3.45 volts. So if you were to substitute 3.45 volts into V3 here, you would then get 18.5 volts at your output. So for the next question, a little bit easier. Consider a signal modeled by a sine wave given as x equals sine of 100 pi t, and what is the appropriate sampling rate to capture this signal? So the sine function has a period which is equal to t which is equal to 2 pi over omega 0, which is equal to 2 pi over 100 pi, equal to 1 over 50, which is equal to 0.02 seconds. And then the inverse of the period is frequency. So frequency is equal to 1 over t, which equals 1 over 0.02 seconds, which equals 50 hertz. And Nyquist's theorem says that in order to accurately sample a signal, your sampling rate must be twice the highest frequency of the signal. So basically it says that your frequency has to be 2 times your frequency in. Your sampling frequency has to be 2 times your frequency in. So on the original test, it gives choices of 25, 50, 100, and 125 hertz. So I would go with 125 hertz because it is the right answer as given by the testing corporation, and it is the best frequency to measure because there's no greater or equal than, it's just greater than. And for the third question, it says the Norton equivalent resistance seen across terminals A and B is most nearly 184 ohms, 200 ohms, 275 ohms, or 125 ohms. So again, you can look at the FE handbook under the source equivalence section, and the Norton equivalent resistance is the total resistance at the terminals A and B when the independent source, which would be the DC battery, or VS, is set equal to 0 or shorted. So you can see here that the 90 and the 150 are in parallel, and then those are in series, which are in parallel with the 200, which is in series with the 75 ohm. So your Norton resistance equation look like 75 ohms plus 200 ohms, which is in parallel with 240 ohms, which would be 75 ohms plus 240 ohms times 200 ohms over 240 ohms plus 200 ohms, which would leave you with 184.09 ohms. Hope this was helpful, and if there's any questions, I'm sure that you can leave them in the comments. Thank you.